Okay, it looks like we have everybody here but one. Just want to make sure you can hear me and see me.
I can hear and see you.
Thank you. Okay, the first thing I'd like to do is let's start off with a little nuclear material science today. We had the quiz that was due ahead of time today. I have not printed them out yet, so I didn't see if anybody wanted to put their solution up for extra credit. Is anybody interested in doing that? If not, I'll put mine up.
If nobody wants to do it.
Okay, thank you for the offer, Joel, but I'm going to see if anybody else first because you've done a fair amount. Not that I want to discourage you, though. Does anybody else want to put theirs up? Okay, Joel, you're on, and I will make you a presenter.
This is the NMS or?
We're going to do nuclear material science first.
Okay. One second, it's loading. Okay, can you see it?
Yes.
Okay.
Okay, we can see it.
So this was a quiz. And he changed the extra credit question.
Yep. Yep.
So I just drew it again down here. And I got the yield for aluminum 1100 for AYB and ARB. And for ARB, it had no yield, so I had to go with the ultimate stress. Yeah. So I drew a free body diagram. So if I had 20,000 millimeters pushing counterclockwise, and these two were 25,000 pushing clockwise, I had to add another 5,000 pushing counterclockwise to make it equilibrium. So I started with so I basically cut right here, the left-hand side. I used my equation to find shear, what is this, shear stress?
Shear stress, yep.
And I got 50 MPa. So if I were to compare it to the yield shear stress for aluminum 1100, it was 55 MPa. So this left-hand side was safe.
Okay, that's good.
When I got to this side, I had to add 10,000 millimeters pushing counterclockwise. So I just plugged it into my equation with the 0.03 centimeters. And I plugged down here too, and I got 236 MPa, which was not even close to being safe. But it was just like 16 MPa over the ultimate, so it's still not safe. unless I did something wrong.
Nope, that's correct also.
And then I cut over here right at the end. And since this one was a hollow pipe, I had to do 1/2 times pi times the 0.02 meters minus 1/2 times pi times 0.01, which is like the meters of the hollow pipe. And I got 1.7 gigapascals, which was so big, it's just gonna like snap it so hard.
Okay, so that's correct also. Before you
So
go on to the extra, does anybody have any questions as to how Joel solved the quiz? Okay, how about, did you do the extra credit?
Yeah.
Okay,
So for the answer, I said the system is not safe because every point after like this point right here, from here on, it's just gonna break and snap and
right.
not gonna work. So only
As
the
long-
left side is the only safe side.
Yep, as long as one section in your system fails, the entire system fails. But as I've mentioned before, you should always calculate the safety for each section, even if you find one right away that does fail, just in case you made a math error. So that's good. So yes, the system does fail because 2 of the 3 sections fail. Okay, and now for the extra credit.
So this credit was, if we filled the hollow pipe at the end, would it be safe or would it fail? So I just, instead of putting minus 1/2 times pi with the 0.1 squared by 4, it was just this one. So that would be 1.6 GPA, which was still really high because he only went down by 0.1 GPA, which is not like that much.
Correct.
So it would still fail, even if it was filled.
Your answer and your logic is correct on that also. So everything on your quiz you did was correct. Any questions again from anyone on Joel's solution to the quiz, including the extra? Yep. Okay. Let me go ahead and unless anybody has anything about the quiz, I'm going to go ahead and release Joe from the presenter so I can open up the camera here. Okay. Alicia, what was your question? Yes. Okay, let's go back to the problem we had. Okay. When you calculate shear stress in a region, and we know that a system that is being torqued or under torsion can only fail by shear stress. Okay, so we also know that shear stress is also equal to G times gamma, where this is the modulus of rigidity, and this is shear strain. So shear stress and shear strain have a linear relationship that's solely due to modulus of rigidity. This is the way that we calculate the stress, but we also know that it has this relationship back to strain. So there's always going to be that relationship. If this value goes up, this value is going to go up, but it's going to go up linearly. I'm going to show you a little bit more application of that today when we lecture on that. But did I answer your question? Okay, ask it again. Okay. Okay. This is the generic equation for shear stress. If we look at a solid pipe, this J is 1/2 pi times R to the 4th. And this R, if we want this to be a maximum, this value for R has to be a maximum. Because if we go back, if I take this and turn it sideways so it's facing U, and I look at the cross section of the hollow pipe so that this part is solid, this is our inner, this is our outer. We know we can calculate as a function of R, we can calculate the stress that is generated, and we know it's a linear relationship, so that if I rewrote this, basically tau is a function of R. The torque is whatever's applied, and J is the polar moment of inertia, which is a physical property that's based on the cross-sectional area. So you give me the cross-sectional area, and it defines polar moment of inertia.
I think I can help answer this question.
Okay.
I think it's going to have more shear stress because when it's hollow, you have to subtract the outer meters that it's gonna have. So it's gonna make the bottom answer smaller, therefore making the total answer like bigger than what it's supposed to be. You know what I mean? It's gonna be divided by a lower value.
Joel, okay. Joel is getting where I was headed. You have a solid piece. This is the governing formula. If you have a hollow section, the only thing that changes is J, which is the polar moment of inertia, and that ends up being this value. So this value has to be, by just looking at it, less than this value, so that if this is less, this has to be greater. And if this is greater, then the strain has to be greater. But oh, yes. Okay. If hollow, less material. So less weight, among other considerations. And again, whether this is solid or whether it's hollow, if it fails, where is it going to fail first? It's the outer circumference. So either way. So if you can make this with less material, you can make it so it weighs less. Because what I was getting at originally is if I plotted the radius versus the shear stress created, of course, exactly in the center, whether it's hollow or if it's solid, the radius is 0, therefore the shear stress is 0. The further I go out, this value increases so that at the circumference, this is the max value. And again, it doesn't make any difference if it's solid or if it's hollow. I have the feeling I've talked around your question, but hopefully I've answered it. Yes. To a solid, yes. Any other questions on what we did? And again, the key to solving these, let me just erase this part. The key to solving any of these, no matter what I gave you for applied torques, is you must do a free body diagram. And then once you've done a free body diagram, look at each section, and you do that by creating a free body diagram for that. And then look at the stresses that are created for each section. So doing this is rather simplistic because we know that there is no plane stress with torque. So for safety, the only thing we have to worry about is shear stress. And again, it's just taking a complete free body diagram, which I think everybody is getting pretty good at now, and then looking at each section to see what is happening within that section. Anything else on that? Okay. The next thing I want to go over is what I had originally had for extra credit on the quiz, but we didn't get quite that where we wanted to on Wednesday. So I'm going to pick this up again. Again, any questions on this before I erase this? Right now, I'm just going to look at one section of length L. If I turn this on in, we'll make it solid. Where that's my radius. If I apply, let's look at a point on here. Let's say I have a point right here, and we call this point A. If I look at it in this view, that might end up being right here. Let's say I apply a clockwise torque on this of 10,000 Newton meters. What is going to happen to this point? I show the torque in this view in this manner. If I come over here, I can sketch that in this manner. This is clockwise, this is clockwise. So what's going to happen is my point A is going to start to move around the circumference. Well, I'll say A prime. And that rotation is going to be a function of the applied torque. If we go back and look at the formula, and again, right now we're only going to look at the exterior or the circumference of the circle. So this is going to be the max value. So if we increase torque, if this goes up, then this has to go up. And this will start to rotate depending upon the amount. So if I apply 10,000 Newton meters and our system is safe, and then I released this 10,000 Newton meters, I make it go to zero, what happens? This goes back to its original position because this is operation in the elastic range. Obviously, if I get to the point where it fails, this is not going to go back to its initial position. So if I increase torque, this point will slowly move around the circle until I reach the point where the system fails. And then this whole cross-sectional area will distort because it'll no longer be circular. If I go back in this view, and I draw a straight line, hopefully I can draw a straight line, directly back to the wall where this thing is fixed, is I apply this torque, and I can see this point A moves to A prime. In this view, it looks like it's going up here to A prime. The point at the wall, since it is fixed, never changes. And if then I connect this point, let me see if I can do that with a straight line. That wasn't too bad. If I look at it in this view, this angle that has been created is gamma. And gamma is the shear strain, which is again tied back to shear stress in that manner. Okay. We know this is unitless. In reality, this angle we can measure in radians, because radians is considered unitless. Okay. We can look and we can establish a relationship that this theta value is equal to R times theta divided by L. So if we measure this, it has a relationship between the radius, theta, and L. L is the length of this, and theta is the angle of rotation of any point on the cross section. So for example, if I look at this example, A has moved to A prime due to applying that clockwise torque. We know that it has created a shear strain that can be measured here. And if I look at connecting where I started with the radius going back to the center, compared to where it's rotated to with a radius, this angle of rotation is theta, which is this theta. If you throw all of those sort of values together, you can come up with a relationship or an equation to evaluate theta. And if you do that, theta is equal to TL over JG. So the angle of rotation by combining these other equations that we had looks at the applied torque the length of the material, J, which is the polar moment of inertia, and then G, which is the modulus of rigidity. Okay. So if we do this calculation and we look at what the units are going to be, so this is going to be in Newton meters. This is going to be in newtons. This is going to be in meters to the fourth. And this is going to be in newtons per meter squared. So if you do a little cancellation here, newtons, newtons, meters to the second divided into meters to the fourth, it's going to be meters to the second, meters, meters, meters a second. So it all balances out. So you're going to get an answer. What are you going to have to do about that answer? This is basically in radians. You're going to have to convert that to degrees. And how do we do that? We know that they're 360 degrees per 2 pi radians. So if we multiply our answer by this, we will have an answer in degrees, which will show you what this answer is in degrees. Okay. So if we look at the example that we have right now, let's say this thing is 10 meters long. Let's say that we've applied 10,000 Newton meters as our clockwise torque. Let's say our radius is 5 centimeters. And let's say our material is aluminum 1100. So if we look up aluminum 1100, and if you have your 3-page handout that I gave you, what is G for aluminum 1100? Anybody?
26.
Gigapascals, right?
Yep.
Okay. Let's substitute that back into this equation and see what our angle of rotation is at the end. So I'm going to erase what I have up here. And I know I'm out to find my angle of rotation, which we said was TL over JG. Okay. The applied torque I have is 10,000 Newton meters. The length we said was 10 meters. J for this particular system, since it's solid, will be 1/2 pi times r to the 4th. But what is r? R is 5 centimeters. And G, which we just said, is 26 times 10 to the 9th newtons per meter squared. If somebody can do that calculation for me, I'll try to match you at the same time. Let me know what you get. To the minus 8. 10 to the 9. To the 1. If I did my math right, I think I got 0.392 radians. Anybody else get that?
Okay.
You got that?
Yeah.
Okay. So in order to correct that, we know that there's 2 pi radians per 360 degrees. So if I multiply that, what do I have for my final rotation?
221.5 degrees.
What direction?
Clockwise?
Okay. Okay. Because we have found our angle, but we need to know the direction. Since this is clockwise, we know this angle is going to be clockwise. So point A is going to move this amount to this position. Actually, it's going to be quite a bit more around, but it's going to move clockwise because of the torque. Okay. Everybody think they understand that. So let's say I came back in this point, and let's say I picked a point that was 4 meters from the end, and I'm going to put it on this same line, and I'm going to call this point B, and I ask you, how much is point B rotating? What formula am I going to use? I'm going to use the same formula for angular rotation because this holds everywhere. Okay. If we go back in and look at the numbers that go into it, what about my torque? Does that change? No, because that's the applied torque. What about the length?
It's now 4 meters instead of 10.
It is now 4 meters because that's the distance. And why is it 4 and 10? Because we typically measure from here because we know this point never moves. It's fixed. If we move down to polar moment of inertia, does this value change?
No.
Nope, because that's a physical property of the cross-section we're given. What about G, the modulus of rigidity? Does that change? No, because that's a physical property of our aluminum 1100. So you're going to come up with whatever this number is. And you also know that whatever that number is, it's going to be clockwise because it's going in that direction. Suppose I came to a different point. Let's solve this. Point C. Let's say point C is 7 meters from the wall. And that when I'm looking at the end, let's say I have a point that this point C here ends up being right here. So instead of being 5 centimeters, this distance here is 3 centimeters. And I asked you, what is the final rotation of point C? So I know point C in this view starts out right here. Point C in this view is right here. And I asked you, after this applied torque, where is point C? Can we do that? You bet. First of all, if we look at it in this view, we know it's going to move up to here because that's showing this rotation per length. If we look at it in this view, we know that this entire line is rotated up to this position. So point C is rotated up to here. So this is C prime. If this was originally 3 centimeters, this is still 3 centimeters because all we're doing is swinging that radius around and we're looking at a point on that. So if we go back to our initial equation and we're looking at point C, has my torque changed? Nope. Has my L changed? Yes. It is now 7 meters. Has J changed? Nope. Physical property of the cross section. Has G changed? Nope. Physical property of the material. So if I do this math, I'm going to come out with a new number.
J didn't change? I thought you had to change it to 0.03 centimeters.
No, that's my next point. So you know that this is still going to be clockwise in rotation. Okay. So to go from C to C prime is the same angle of rotation as going from A to A prime because we're keeping the radius constant. So yes, A moves to A prime, so it's moved further around on the circumference. C has moved lesser distance to C prime, but the rotation is still for both of those theta. And theta is this calculation. How are we doing? You think you understand this? Okay.
Okay, wait. So what you're saying is if you want to find out C, even though it changes in like the radius.
Yep.
So
I have changed, in other words, in this view, C is 7 meters from the end. And then I'm going to apply the torque. And C is actually going to move up to C prime in this view. If I turn this, rotate it towards the room, C, which starts out here, is going to rotate to C prime. So you see it here in this view, here in this view.
But you're telling me that doesn't matter, basically.
It doesn't matter because what you're really doing is rotating that radius. So I'm rotating that radius from 0 degrees. Once I apply the torque of 10,000 Newton meters, it's going to rotate up to here. So if it's A, it moves to A prime. If it's C, it moves to C prime. But it has rotated the same amount theta. This enclosed angle between the two radiuses is still the same. And of course, the only thing that will vary on that is where you are on the length of the material. So if I had another point out here that, let's say I want to know what's the rotation at 8.5 meters from the end, we call this point D. In this view, I know that D has moved up to here. If I look at it over here, D is going to be here. It's going to rotate up there to D prime. But this angle of rotation is still the enclosed angle between those two radiuses. And if I go all the way out to the end, A is rotated to A prime, which we've already proved. Everybody sort of getting a handle on that? Okay. Any questions?
Yeah, I understand the concept. I was just confused because I thought J was going to change, but I guess it doesn't.
Professor, could you go over where you got the 221.5 degree figure from?
When we did our math for the original rotation, at point A to go to A prime, and we wanted to find out that was. We threw in these values. We came up with this answer, which was in radians. And then we needed to correct radians to come up with degrees. So we know that 360 degrees is 2 pi radians. So I asked somebody to do that calculation, and this is what they told me the answer was. And we know it's clockwise because the torque was applied clockwise. Any questions? Okay, let's take this up a notch and let's look at multiple sections. Any questions with this before I erase it? Okay. Okay, we'll start off with baby steps.
Some people are saying they didn't get 221.5.
Say that again, Joel.
Some people are not getting what you're getting.
Okay.
Oh, never mind. Never mind. He's
No. What are those people getting?
22.5.
22.5 degrees?
Yeah, 22.5.
Okay. Well, then there was a math error. Who gave me that original answer? Heather?
It was me. It was a parentheses error.
Okay. All right. Let's look at what we have now. We're going to take this up a notch. So let's say have a 2-section system, and this length is 6 meters. This radius is 4 centimeters. Let's say this length is 2 meters. And this radius is 2 centimeters. Let's say this material is aluminum 1100. Let's say this material is aluminum 2014. let's say I have a point A here on the end. Have a look at cross section here on the end. This is point A with that radius of 2 centimeters. Okay. I am now going to apply a counterclockwise torque of 10,000 Newton meters. And here I'm going to apply clockwise torque of 7,000 Newton meters. Okay. I could come back and ask you a couple of questions. For example, is our system safe? Next question.
Can I interrupt for just a question? So where is the 7,000 Newton meter clockwise torque? Where is that point on there? At the connection between the two?
Applied right at the intersection between the two.
Okay.
Is our system safe? And then finally, what is the final location of point A? Okay. So this is our system, and this is what I've asked you to find out. So what I'm going to do is, first of all, I'm going to move this further up just to give me more room to work here. Okay, so I'm going to erase this. Okay, what's the very first thing we need to do?
Free body diagram.
Free body diagram. So let's do our free body diagram. So we sketched a member. Drawing any given forces, moments, torques, couples. How many do we have? We have 2. Okay. So we have 1 attachment point. So we know whatever we add in the way of forces, moments, torques, couples to the system to put it in equilibrium, we can only add it at this point, only at that point. And the only thing we can do to calculate whatever we're going to do is the 6 equilibrium equations. If you look at this, we have the 3 force equations. Sum of forces in the x direction equals 0. Sum of forces in the y direction is equal to 0. Sum of forces in the z direction is equal to 0. There are no axial forces, so this is automatically satisfied. We also know that there are 3 moments. We have sum of moments around the x-axis has to equal to 0. Sum of moments around the y-axis has to equal to 0. Sum of the moments around the z-axis has to equal to 0. In looking at this, which moment are we concerned with?
The X moment.
Around the x, the y, or the z?
The X moment.
The x-axis moment. So if we look at this, these are making our system want to rotate around the x-axis. So the only one we're interested in is this guy. So we know that the sum of moments around the x-axis must equal 0. So the clockwise have to equal the counterclockwise. What do we have? This guy is counterclockwise for 10,000 Newton meters. This guy is clockwise for 7,000 Newton meters. 7,000 is not equal to 10,000. So in order to balance that out, we have to have 3,000 Newton meters. So the 10,000 is equal to 10,000. This has to be clockwise, and the only place we can add it is at the attachment point. So that is our complete free body diagram. Okay, that's step one. The next thing we're going to do is, what about our safety? And we know since we have two materials, we're going to have to do two calculations. So we're going to go back, cut this anywhere, just to the right of there, just to the left of there, so that we're in the aluminum 1100. We're going to do a free body diagram of the left-hand side. Okay. We're going to complete that free body diagram. So we've sketched it. How many givens do we have? We only have this guy for 3,000. Okay. We have one attachment point where this attaches to the rest of the bar. So for equilibrium, we can only add a moment there to balance it out. So this is 3,000 Newton meters. This section is in equilibrium. We can now go and see what kind of stress is generated. So if we look at the shear stress that is generated in my aluminum 1100 section, we know that it's equal to the applied torque times R divided by J. What is the applied torque? That is the torque that occurs anywhere just to the right of here, just to the left of there. So no matter where you cut this, you're going to get the same value of 3,000 Newton meters. Let me erase this. So this guy is 3,000 Newton meters. What about R? We know that the maximum value of this, which we're concerned about for safety, is always at the outside circumference. So this value is, the radius is 4 centimeters. 4 times 10 to the minus 2 meters. What is the polar moment of inertia? The polar moment of inertia is a fixed property based on the cross section. So we know that for a solid pipe, that's going to be 1/2 pi times R raised to the 4th power. Okay. If somebody has a calculator, let me know what that value is.
I got 30 MPa.
30 megapascals?
Yeah.
Okay. Anybody else get that? Anybody else?
I got 29.8, so basically the same.
Okay. So, is our system safe? We're going to compare this to tau yield. Tau yield for aluminum 1100. And how much is that?
55.
55 megapascals. So, is our aluminum 1100 safe? The answer is yes. Okay. So, I'm just going to make a little middle note in here that we had a value of. Okay. Any questions on what I did? Okay. We still have to look at the safety for the last one. So we're going to do back and draw another free body diagram, do another shear stress calculation. So this time I'm going to cut it here, anywhere, just to the right of there, just to the left of here. And now I'm going to do a free body diagram of this left hand side. If I do that, I've sketched the member. I'm now going to sketch in any given forces, moments, torques, couples. So here I have 3,000 Newton meters clockwise. Here I have 7,000 Newton meters clockwise. I have one attachment point for this left-hand side. So what must the moment be, or the torque be, that I'm applying here to put the system in equilibrium? In what direction?
10,000 Newton meters
10,000 Newton meters, what direction?
counterclockwise.
10,000 counterclockwise. Okay, so that is a complete free body diagram for this section. I now can go and do my safety calculation. I know that shear stress for this aluminum 2014 is the applied torque times the radius divided by J. For this region, we've just shown that this applied torque anywhere in this region is 10,000 Newton meters. What is the R? We know that if this thing fails, it's going to fail at the outermost radius, which is on the circumference. So this is 2 centimeters. What is our polar moment of inertia? Again, it's a solid pipe. So again, physical property is 1/2 pi times R raised to the 4th power. So somebody will let me know what that value is.
I got 796 megapascals.
796 megapascals. Anybody else get that?
I agree.
Okay. So we're now going to compare this to the yield value for aluminum 2014, and that's on that little table I gave you. What is that value?
230 megapascals.
So is our system safe?
No.
No, because this is greater than the yield value, so it's going to fail.
I got a question.
It's going to fail in our aluminum 2014 region. Yes, Joel?
So, I didn't look at the maximum, but if the maximum, let's say, is 300, would that be not 300? Oh, that's
Say that
700.
again?
Let's say we get one. That's 250 megapascals, right?
215?
No, 250. So it goes over the yield, but it's not over the maximum. Would that be safe or no?
Remember, there's 2 values in the back, and this is the same. Okay, I'm going to use the sketch for plane stress very quickly. Any questions on what we did here? Okay. And that value was, excuse me a second while I write this in here. Okay. If you go back and you remember, if we look at plane stress versus shear stress, if we look in the areas that have tension, we had a plot that looks like this. This is sigma yield. So if you apply an axial force, and this is in tension, it will move up this. If you release a force, it goes back down. Apply a bigger force, it goes up. Release it, goes back down. When you go past the yield value, it sort of meanders around and will finally get to a point where it is ultimate. So anywhere you go from no applied axial force to a force that just reaches the yield value, this is safe, because if you release it, it'll always go back. If you go beyond, if you add more axial force and it moves over here, once it goes beyond here, there's a chance it can fail. Will it fail? Maybe yes, maybe no, depending on other factors. But whenever you release the force, it does not go back here and goes down. It goes down parallel to that original plot so that you will always have a permanent offset. So in other words, if you had an intention, the thing is going to be longer than it was when you started. It's not going to go back to its initial condition. If you apply additional axial force, it'll go back up here, back down here. But again, anytime it's beyond here, it can fail. If you ever apply enough to get it to this point, to the ultimate value, it will absolutely, positively fail. No questions asked. So what we do whenever we consider safety, we want a factor of safety. So we always consider for safety to use the yield value. And this is for either plane stress or shear stress. Okay. This again was for tension. So in other words, if we had this member and we put it in tension, if we put it in compression, because we're only working with metals, you would see a mirror image of this thing on this side. So this is for compression and this is for tension, but they behave exactly the same way. We still always use the yield value to calculate safety. Everybody on board with that? Okay. Let's go back to my original problem. So we've determined this section is safe, this section is going to fail, but I still want to go and find out what is my ultimate rotation for A. Remember, our equation for rotation is TL over JG. And we can do that because when we start with just one section, we know that at 0 for length, which is at the wall, it's fixed, it's attached there, so my angle of rotation is 0. It's not going anywhere. If I have two sections, what am I going to do now? If I look at this, my final rotation, we could look at the sum of what's going on in each individual section. So it is TL over JG, where I'm going to let I go from 1 to how many number of sections we have. So I put a little I here, little I here, little I here, little I here. So if we want the final rotation of point A, and I look at this summing device, how many calculations am I going to have to do here?
2.
2, because I have whatever's going on in this section, and then I have whatever's going on in this section. So if I spell this out, this is going to be T1L1 over J1G1, where this is section 1, plus T2L2 over J2G2 for region 2. And if I add this to this, I'm going to find the total rotation of A for our system. So now we can go back and just plug in values. So if I look at the torque that's applied in region 1, what was it? We said that it was 3,000 Newton meters. What was the length? The length was 6 meters. What was J? J is the physical property of the shape of the cross section, which is going to be 1/2 pi times 4 times 10 to the minus 2 meters raised to the 4th power. And G for aluminum 2600, if I remember right, was 26 times 10 to the 9th newtons per meter squared. Okay. Let's go look at the second region. What was the torque applied here anywhere in this region? We said it was 10,000 newton meters. What is the length? The length is 2 meters. What is J? It is the polar moment of inertia for this unique cross section, which is going to be 1/2 pi times r, which is 2 centimeters, 2 times 10 to the minus 2 meters raised to the 4th. What is the modulus of rigidity for aluminum 2014 off your table?
27 times 10 to the 9th.
27 gigapascals, so 27 times 10 to the 9th newtons per meter squared. Okay. We are ready to rock and roll and do our calculation except for one thing. What do you think that one thing is? Okay.
The direction of rotation.
That's right. It's the direction of rotation. And to do that, we have to see what is going on in each one of these regions. We know the torque that was found to be operating within that region, 3,000 here, 10,000 there. But we need to go back and look at what direction is that going. And we need to set up a little sign convention. Okay. And then what I like to do, and you can do this any way you want to, is I like to say torque clockwise at end creates clockwise rotation. So then I look at the torque in each section. So what I'm saying here is, let me see if I can sketch this here very quickly. Let's say I only had one torque applied. Let's say clockwise here I had 5,000 Newton meters. So I look at my free body diagram. Hopefully you can see if I only have that one torque and we're looking at rotation along this straight line, no matter where you go, everything is rotating clockwise. At the wall, it's going to be 0, and then it's going to be move more and more. So if I draw my free body diagram for this, this goes 5,000 Newton meters here. When I cut it here, I'm going to get 5,000 Newton meters here. So by setting up my little sign convention, if I have the torque being clockwise at the end, I consider that to be positive. So then I go back in each section to look at what the value generated is. In this case, it's 5,000. This is also clockwise. So this sign that I'm going to put on the torque will be plus. When I go back and look at the next section, okay, I've got this 5,000. This has to be 5,000 again. Again, this is clockwise in the cut. I've established that clockwise is positive. So this value, when I plug it in the equation, is also going to be positive. So let's go back and look at our particular case. So if we go back to our first section, we had 3,000 Newton meters going in that direction. So when we apply equilibrium, this is 3,000 Newton meters. That's the 3,000 Newton meters we put in this equation. Now the question is the sign going to be positive or negative, and why?
Negative, because it's rotating in the counterclockwise direction.
It's negative because this is going counterclockwise, and our little grid we set to start with says you apply clockwise torque at the end, clockwise is considered positive, and we're comparing everything back to this. So this is in fact negative. We go back and look at the next section. Okay, so we had one. Okay, and we had our 10,000, but the 10,000 went this way. Okay. So what sign are we going to use for this 10,000 when we put it in our equation?
Negative as well?
Negative again, because again, we've established clockwise at the end as being positive. This torque is counterclockwise, so it's going to be negative. So you're going to do all this math, and you can just look at this and see the final answer is going to be negative, whatever it is. Has anybody done that, all this math?
I got negative 3.17 radians, right?
Okay, you didn't correct it yet. So this is 3.17 radians. Anybody else get that? And again, you really need to be working these with your calculator to make sure you're getting the same values. If you're getting something different, then we can explain what's going on. Anybody else get 3.17 radians? Or let me know what you did get.
I got 3.12 radians.
Okay, close enough. So we're going to multiply this times 2 pi radians for 360 degrees. So what's the final rotation of my point A? It's going to be negative. What's it going to be?
I got negative 182 degrees.
Anybody else get that? Okay, I'm going to assume that's correct. So what that tells me is point A has rotated 182 degrees counterclockwise. So this is my final A prime. Let's say I went and I picked a different point. Let's pick a point . 5 meters down from here. And let's call this point B. I could ask you, what is the rotation of point B? Okay. We'd go back in, and again, if we look at our equation, if we go back to this first section, T is the same, L changes because it's now 5 meters instead of 6. My polar moment of inertia is not changed based on the cross section. G is not changed based on the material. What do we do with this part? That is 0 because we're looking for just the rotation at point B. So we calculate whatever that is. It's still going to be negative. Multiply it by 360 degrees for 2 pi radians, and that'll tell you how much this point B rotates. So we can find anything that we want to do. Okay. I have a quiz made up for you. So I'm going to go back and send you the quiz now, ask you to look it over, and yeah, I've just sent you the quiz. Let me give you a minute or two to get it and look it over. If everybody has got it, everybody have it?
Yes.
I got it.
Okay. So I've given you a system that has 3 parts to it. All the material is aluminum 1100. The part where it leaves the wall is a hollow pipe. It's 2 meters long, and the radiuses are for outer and inner are 3 and 1 centimeters respectively. The next section is 4 meters long. It has a radius being solid of 6 centimeters. The third section is 3 meters long, has 4 centimeters. I've established where point A is. At the very end, I've applied 16,000 Newton meters clockwise. If you go back to the intersection between the first and second section, I've applied a torque of 10,000 Newton meters counterclockwise. And this is worth 14 points. I've asked you, is our system safe? And justify your answer. And then I want to know, what is the final location of point A? If it's rotated clockwise, counterclockwise, if so, how many degrees? That's the quiz. And then for extra credit, if we fill the hollow pipe in so that it's now solid, does point A rotate more, rotate less, stay exactly where it is, circle one of those 3, and then justify your answer? That is the quiz, and it'll be due on Wednesday. Any questions on that? Okay, let's take a little over a 10-minute break. I'll see you at 5 after 12. First thing I want to do is do the reactor theory quiz, and then I'm going to start lecturing on neutron activation. So I'll see you back here at 5 after, unless you have any questions about the quiz or what we've done so far for point 20.
Professor, can I ask a question? So for point B, do you add in that second part, or do you only calculate up to point B? So you'd only do like T1?
And this one? And this one?
Yeah.
Yes. Okay, we only go to point B, which is this guy, because you're not worried about what goes on out here.
Okay.
In other words, this part doesn't have any bearing on what's happening to B.
Okay, thank you.
Any other quick questions or any questions? Okay, I'm going to turn my camera and mic off. I'll see you at 5 after. And again, do I have a volunteer that wants to put the reactor theory quiz up when we come back? If not, I will do it. I'll let you think it over. If anybody wants to do it,
Professor, I can do mine. This is Kira.
okay. All right, Kara, what I'm gonna do is before we leave, I'm gonna make you a presenter. And you can at least get things set up. And then when we come back at 5 after, you'll be ready to rock and roll.
Okay,
See
what
you
time
guys
are we
at
coming
5.
back?
I have right now 7 minutes of 2. We're gonna come back at 5 minutes after. I'll see you guys then.
I'm ready whenever you guys are.
Okay. Yep, I got 5 after, so Karen, how about it, please?
All right, so let me see here.
Okay,
Can everyone see?
I can see it.
All right,
Yeah, I
so
can see it.
to start, we were given the initial amount as 8 times 10 to the 18th newtons per per centimeter squared times seconds. And we were given 35 degrees Celsius. And we have the same elements as our last quiz, which were MN 55 and TA 181. To first, I converted the Celsius to Kelvin, so I got 308 degrees Kelvin. We were given that the probability of scatter in epithermal was 1.9 barns, and we had to calculate the probability of absorption epi. So I did 13.2 times square root of pi over 2, and then I multiplied that by the square root of 293 over 308, and I got 11.4 barns. To find the total probability, I added those two together, and I got 13.3 barns. And to make that into centimeters cubed, I made it 13.3 times 10 to the 24 times 10 to the negative 24th centimeters cubed. The density is 7.2 grams per centimeter squared, and the atomic mass is 54.938. To find N, we multiply the density times Avogadro's number and then divide it by atomic mass. And I got 7.9 times 10 to the 22nd. We already know our initial flux, which was 8 times 10 to the 18th newtons per centimeter squared second. And our length was 4 centimeters. So to find the epithermal flux for that part, I did the initial flux, 8 times 10 to the 18th newtons per centimeter squared per second, times e to the negative 7.9 times 10 to the 22nd times 13.3 times 10 to the negative 24th centimeters squared, and then multiplied that by 4 centimeters. And I got 1.19 times 10 to the 17th newtons per centimeter squared per second. And then I went on to TA 181. I did the same thing that I did for MN 55 to find the probability of absorption for epi. And I got 18.1 barns. We knew that the probability of scatter was 6 barns. And then to find the total probability, I added them together. So I got 6 barns plus 18.1 barns, and I got 24.1 barns, which correlated to 24.1 times 10 to the negative 24th centimeters squared. We knew the density was 16.6 grams per centimeters cubed. And the atomic mass was 180.948. The N value, we also calculated that in our last quiz, and it's 5.6 times 10 to the 22nd. It's the same formula as we did for the MN55. So for our initial flux of this one, we use what we got for the final flux of the MN55. So we got 1.19 times 10 to the 17th newtons per centimeter squared per second. And then we knew that the distance was 6 centimeters. To calculate at the detector, we multiplied 1.19 times 10 to the 17th newtons per meter squared, centimeters squared per second, times e to the negative 5.6 times 10 to the 22nd times 24.1 times 10 to the negative 24 centimeters squared, and then multiplied that by 6 centimeters. And then we got 3.62 times 10 to the 13th newtons per centimeter squared per second. And that's what I got.
Okay, that's ballpark what I got, but again, depends on how you round off the numbers. Does anybody have any questions for her on her solution? Did you do the extra credit?
No, I don't.
Okay. Does anybody have any questions for her? Yes. I misspoke.
Yeah, I did.
Did anybody do, thank you, Kara. I'll take you off and put you back in the other group. Did anybody do the extra credit that wants to present it? If not, I will. Nobody wants to do it. Okay? If you take the flux, which is in neutrons per square centimeter per second, and if this is your target, your flux is coming in that way, and your detector is here. If I look at this surface, this is the surface area that the flux sees. So if I multiply this times the surface area, and we said this was 5 centimeters by 5 centimeters, this will cancel out with your square centimeters there. We said that this was going to run, we looked at time, we said this is going to run for 10 minutes. And we know that 1 minute is equal to 60 seconds because we want to cancel this, and then we want to have this time cancel with that time. And then if we look at the efficiency, we said that that was 96%. Okay. If we multiply this times our flux, and if you use the flux as it's exiting, and you could also use the flux as it enters, but then you'd have to account for its attenuation and loss as it goes through. So I had a slightly different value. Instead of, I think she had 3.7 or something, I had 4 times 10 to the 13th neutrons per square centimeter per second. And then when I multiplied this as here, so that you'll only have neutrons as your final answer, I came up with 5.76 times 10 to the 17th neutrons would be measured by the detector. Any questions on that? Okay. If I do a quick summary for where we stand right now. Okay. Oh, before I do that, During the break, I got a call from Professor Dorn. He apparently, I know that you do not have a lab this Friday. Apparently he was not feeling good over the weekend. He had a headache, whatever. And just to make sure, he went down and tested him, was tested for COVID. And sure enough, he did test positive. So it's not going to impact anything this week because you're online for your class and the lab, you're not having a lab this Friday. It could potentially impact things for next Friday. We're in the process now about finding out what the protocols are if you've tested positive. And I want to say that it is 2 weeks that you have to stay out. If that's true, then next Friday, he's going to have to come up with something rather than an in-person lab. But we're still exploring that possibility, just for your planning. The other thing I wanted to mention is by Friday of this week, I have to come up with midterm grades. And up until this semester, faculty have always been able to either put in a letter grade or put in a P for passing. And historically, most of the faculty here have used a P for passing because depending upon what you may or may not have done so far for lab reports, that type of thing, we know that you're participating, we know that you're doing well, but a midterm grade really does not mean that much. The academic dean has decided as of Friday that he wants you to have a real letter grade. Part of the thing we had a meeting about earlier today for the department was we're trying to get that changed back to the way it used to be. So hopefully that will be changed back. And so you would be seeing a P, at least for me, for your courses and labs. For example, we haven't even done any URI labs, so how can I come up with a grade for you on that? If you are, in fact, though, failing due to bad quiz and exams for my 2 courses, I will put in a letter grade if you're getting a D or an F right now, just so you'll sort of know where you stand. If he makes us go with a straight letter grade, since really all I have for you is 1 exam in each area plus 5 to 8 quizzes, I'll probably just give everybody across the board a B rather than try to calculate what it is. Hopefully I'll have more to tell you about this on Wednesday. The only thing I'd say right now is if you are flunking or getting a D in either of my 2 courses, that would show up as the F or the D accordingly. Okay. To go back to neutron interactions. We know if we have a flux strike a target, the neutrons will interact with the atoms in the target, and we could have losses, and the losses could come from scatter or absorption. We developed an expression to show the probability of this, and this was sigma, and the probability for scattering would be sigma S. Scattering for absorption is sigma A. We both typically look at total, which is the summation of the 2. Anything that doesn't scatter or doesn't get absorbed will in fact reach the detector. We know that if we look at absorption as a function of energy, if we look at absorption cross-section, it looks something like this, where this is called the Doppler effect or Doppler broadening. If we look at scattering cross-section versus energy, it tends to be fairly constant, but if you look at all materials, it has a slightly downward slope. We can look either of these values up in the Barn book. And these are 3 massive volumes, which each page is like tissue paper, and it has the absorption or the scattering cross-section for any material at any energy of neutron beam. Tabulated in the back of your book. We have different values. So if we look at the back of the book, for absorption, we only have sigma A for thermal neutrons. As it turns out, if we need to find sigma A for epithermal, this is going to be sigma A for thermal value times the square root of pi divided by 2 times the square root of 293 divided by T, where this is the absolute temperature of our flux. Okay. Typically, room temperature is 293 degrees Kelvin. That's where that number comes from. And as T changes, we need to change in this equation to come up with the representative absorption cross-section to use depending upon the temperature. There are also relationships between T, E, and V, where this is the temperature, this is the energy, and this is the velocity. If you go back to the diffusion of neutrons in a room, we had a Maxwellian distribution that is skewed to the right. And again, if we let all the neutrons from one location diffuse throughout a room, it will take on the properties of the air in the room, and there will be a most probable value. And we can relate that to temperature, energy, or velocity. This curve would still look the same, and this is the most probable value. If I did this one for room temperature, this T is 20 degrees C, which is 293 degrees K. Our energy, which is 1/2 mv squared, we showed was 0.0253 eV. And we know the velocity of a thermal neutron is 2,200 meters per second. There were relationships given you in your textbook. So for example, the quiz that I gave you that you just turned in, I said the temperature was what? 35 degrees C. So you could automatically go in and change the temperature and adjust your absorption cross-section for that temperature. I could have, in fact, gone back instead said the velocity was 2280 meters per second. There is a relationship between velocity and temperature. And in your textbook, if you have a textbook with you or handy, you can go and look on page 204. Okay. And if we look at equation 812, it says that the most probable velocity is equal to 2kt divided by m raised to the 1/2 power. So if I know what my t is absolute, this is Planck's constant, this is the mass of the neutron, I can find out the most probable velocity. If we go down to the next equation, which is 813, we see a relationship between kinetic energy, most probable, and that's equal to kT, where this is absolute temperature, this is Planck's constant, and this will come up with the corresponding kinetic energy for most probable. So if instead of giving you the problem I did where I gave you 35 degrees C, so you can just immediately adjust that. If I gave you the velocity is 2280 instead, from looking at that, since it's greater than 2200, you know it's epithermal. So you could go back in here, substitute this in, come up with a value of t. This is automatically going to be absolute, which you can plug in here. If I told you instead that the kinetic energy was 0.5 eV, I could plug that back into here and come up with a corresponding temperature. There is, however, another shortcut that you can use, and it's sort of a dimensional analysis type thing, which I will share with you. And let's look at the kinetic energy one. Kinetic energy most probable is equal to K times T most probable, okay? This is a fixed formula. So I can look at any two values and compare them by doing a dimensional analysis. So for example, if I look at thermal, I know that this energy, which is 0.0253 eV, is a function of the temperature, which is K times 293 degrees K. I know that this expression is throughout. That equation is good anywhere. So if I divide this equation by itself, but this time I'm looking at a different energy, okay. If I divide something by itself, I haven't changed the value. So EVs cancel EVs, Ks cancel Ks. So with this very simple equation, I can come up with the temperature that is the most probable for this particular energy, which is going to be 0.5 times 293 divided by 0.0253. Whatever this value is, it's going to be absolute, and I could plug that value into here to adjust my A for epithermal. Everybody with me? Anybody not with me? I could do the same thing for velocity. What I know is that velocity most probable is equal to this, but this is really a constant because it's Planck's constant times the mass of the neutron. So what I really know is the most probable velocity is a function of the square root of the temperature. Again, if I utilize that equation, numerical analysis, and I divide it by itself, I have not changed its value. So if I look at a thermal value, I know that this is 2,200 meters per second. I know this is 293 degrees K. If I asked you to adjust it for (280) excuse me, 2,280 meters per second. Cancel, cancel. So my temperature to the 1/2 that I'm looking for is going to be 2,200 meters per second divided by 2,280 meters per second. I'm doing my multiplication wrong, sorry about that. So this is going to be 2,280 meters per second times the temperature, which is 293, which is absolute, raised to the 1/2, divided by 2,200. So I can use this to find the value for T, to plug into here, to adjust my flux, which I know is epithermal, to have the correct value to use for looking what's happened for probability of interactions. So I could give you T, I could give you V, or I could give you KE, and you can still use that equation to adjust the formulas accordingly. Any questions on that? Okay. Okay, so hopefully now you could handle any flux, thermal or epithermal, going through any material, any groups of materials, to look at interactions and to measure total amount of flux that's getting through, total amount of neutrons that are going through. The only other thing I wanted to mention, and this goes back to the quiz presentation, is we said that the flux at the detector, okay, is equal to the initial flux. And if we have more than one section, in this case we had two, we had the manganese and the tantalum, okay. And so what Kiera did is she just looked at the manganese contributions, calculated this, found this, but this is not really what's at the detector. This is what shows up at the boundary to then go through there. So to find out, in this case, what is at the detector, I'm going to use this value, which is what has survived the manganese, and then I'm going to do a similar calculation looking at what happens to tantalum. So she did this calculation, took this value, plugged it in here, did this calculation to come up with a final answer. Remember, we have showed you that when you have multiple materials, let's say I added to this iron, let's say I added to this aluminum. If you started to do this, you're going to have to do 4 calculations. And whenever you have a chance of doing a calculation, you have a chance of messing it up. So when you look at it, we knew that the flux at the detector is equal to the initial flux that strikes our target times e to the minus, and then we can sum up what is going on through each of these materials. So we could say this is N sigma T X for my manganese plus N sigma T X for my tantalum plus N sigma T X for my iron plus N sigma T X for my aluminum. So you basically, instead of doing 4 calculations, you narrowed it down to 1 calculation. You still have to find out each of these values. N, number density, is always going to be density times Avogadro's number divided by the atomic mass for whatever that material is. X is the thickness that it's going through. Sigma T is always sigma A plus sigma X. And if it is thermal, we know that these values are in the back of the book. If it is epithermal, we know we have to adjust this by our equation. This value for epithermal is in the back of the book, so we can just add that to it. So we have a way of looking at thermal, epithermal fluxes going through any sequences of materials to see how they are attenuated before they reach a detector. The other thing we noted is if you put this as the flux going through manganese, then tantalum, then iron, then aluminum, we showed before that you can actually change these out. So we can make this go through tantalum, then iron, then manganese, then aluminum, and you're going to come up with exactly the same answer because these powers are all additive. Everybody feel comfortable on what we've done so far with that? Okay. The next topic I want to start today is neutron activation. I'd originally planned to give you a quiz tonight on that, but we're definitely not going to get finished with that in time. So I'm going to make a presentation today on neutron activation. In fact, neutron activation will be the very first experiment you do when you go to University of Rhode Island later in November. Then I'll lecture some more on Wednesday, and I'll give you the quiz then on Wednesday, which will be due the following Monday. Anything on the overview I just gave for what we've done so far? Okay. Okay, let's look at neutron activation. What is neutron activation? It is the use of a neutron flux on a target to create an isotope to use typically in medicine or industry. So what we're going to do is we're going to use a neutron flux. We're going to strike a material, and then that group of neutrons are going to activate that material to create an isotope that is of interest to us for either industrial or medicinal purposes. Okay. So your book goes through an example where they have used silver. What I'm going to do is I'm going to make the presentation as to how we develop this, use it a little bit as an example, and then we'll stop there today with any questions that you have. So I'm going to pick something different. So I'm going to have a flux coming in, and let's make make our target good old niobium 93. When this flux strikes these atoms of niobium, it will create, by neutron absorption, niobium 93. Niobium 94. This is our desired isotope of interest. This is the one, for example, that we might want to use in medicine for lung scans. So, if we look at what is really happening, and we call N1 to be the number of atoms of niobium 93 and time equals 0, we let N2 be the number of atoms of niobium 94, then we would try to develop an equation to define N2, which is number of atoms of niobium 94. If you remember, a couple of weeks ago, we talked about how you would develop that equation, and we looked at that for a number of different reasons, and we basically look at the rate of change of time with whatever the topic is, and try to set up a word equation, and then develop that into a mathematical expression that we can solve. So I'm looking at what happens to my niobiums as a function of time. Whenever we have this, we can automatically say that any change of this with respect to time is a function of production minus loss. If we can find out what that is, if we can make these words into expressions, then hopefully we can solve this. So let's look at this. Where or what is the production? Where does the production of niobium-94 come from? It comes from the absorption of neutrons by niobium-93. If you want to follow this presentation, we can go to page 209. Okay. So for the production, we have created from the absorption of neutrons by our niobium-93. Can we come up with an expression for that? Yes. This is going to be equal to the flux that we have times the number of atoms of 1, which is our niobium-93, times the cross-section for absorption for our niobium-93. So the flux is going to strike a number of atoms. There's a certain absorption cross-section or probability for an interaction. This is going to create the production of our niobium-94. Next, we look at the loss. So, how many losses do we have for the niobium-94 once we've created it? Since we know it's a radioactive isotope, we have its natural decay. What else do we have? We have the possibility that it can absorb neutrons in the flux. So you have a flux that creates niobium-93s. That uses 93s to create niobium-94s. Once you have these, they're naturally going to start to decay. But also because these are there and they're in the flux, they can remove neutrons that would change the niobium-94s. They can absorb neutrons. And then what would they become? They would become niobium-95s. But we're not after niobium-95s, we're only after niobium-94s. So we have a production through the absorption of a neutron by 93 to create 94s. And then once we have 94s, it will decay naturally, but it can also absorb neutrons in the flux to become something else, so they're not your desired target. Okay? So could we come up with expressions for this? And the answer is yes. So its natural decay would be lambda times N2, where this is decay constant. Okay. And the other would be the flux times the number of 2s that you have at any one time, times the absorption cross-section for that particular isotope. So we have a production, we have two losses. So if we put those together, so we have dN2 dt, where this is niobium 94s. And this is going to equal the production, this is the flux, times the number. So this is our flux. This is the number of atoms of niobium 93 that we start with. And this is the absorption cross-section of our niobium targets. We're then going to subtract the natural decay, which would be lambda 2 times N2. This is the decay constant. What is the decay constant? It is 0.693 divided by the half-life. But the half-life of what? The half-life of my niobium 94, because that's the one I've created. Where do I find this? This is in the tables at the back of the book. It's a physical property. And then what about the absorption? So then we're going to have the same thing we have with this one. It's going to be the flux, but this time times the number of 2's, because again, we're looking to see how niobium 94 is absorbing neutrons to become niobium 95, which we don't want, times its absorption cross-section that's unique there. So this is the flux. This is the number of niobium 94s at any particular time. And this is the absorption cross-section for my niobium 94. Where do you get this? You get it in the back of the book. So, if I integrate this over time, from time is equal to 0 to time is equal to infinity, integrate this also, you come up with the equation of interest, which is 8.25 before we do that, you can do a little bit of simplification. If you look at this, the one common thing you have is N2. So if you pull N2 out of that, this becomes minus lambda 2 minus the flux times the absorption cross-section of 2, all of this times N2. We can pull the minus out, so that it becomes nothing has changed at the start. And then since all of these are minuses, minus N2 plus flux sigma A2 times N. So we take in this equation, combine this like term, come up with this. And this is what we're going to integrate over time. And if we look at this, this is the natural decay constant of our niobium-94. This looks at its loss to becoming 95. So we could combine those two together and call this lambda 2T, which is equal to this. This is the effective decay constant for our niobium-94. So the equation that we started out here, we can shorthand to this. And then if we solve that, we're going to come up with equation 8.25. So if we solve this so that we have a function, number of N2s, it's obviously going to be a function of time. So if you solve this is the equation that we've taken with shorthand to come down to that. If you solve this, this is equation 825, and this comes out to be the flux. They've done a little additional shorthand there, but N1 sigma A1 divided by this lambda 2T, which is the effective decay constant, times 1 minus e to the minus lambda 2T times T. So this tells you that the number of niobium-94, which is your out to produce, is in fact a function of time, and we know that because they're being produced and they're being lost. And it is equal to this equation. If you plot this equation as N2 as a function of time versus time, we know that if time is equal to 0, we know we don't have any N2s because the neutron flux has not had a chance to interact with the initial atoms. Once it does, this will start to grow. So this is a plot of this equation. Okay. It will reach, after a certain period of time, an asymptotic value. That asymptotic value is N2 is equal to just the first part of this, which is the flux times N1 sigma A1 divided by lambda 2T. So what this tells you is if you put this niobium-93 in a neutron flux and you turn on the flux and let the reactor hum away and produce neutrons, it will continue to produce niobium-94s, but it will reach an asymptotic value. So as you go on in time, you're not really creating any more niobium-94s. So you typically try to find out exactly what this time is here, where you'll sort of have a maximum value, and then you want to extract these, package them, ship them, send them off.
Professor, when you did the N2T equation, you put 1 minus e to the negative
Lambda transition T, where lambda transition T is lambda 2 plus the flux times the absorption cross-section for.
Yes, I understand that, but what is the transition and what is that symbol? It's a little bit blurry.
2T.
It's lambda transition T, but what is that? It says
This is
2T.
just denoting that this is the effective decay constant.
No,
for-
Professor, I'm talking about the bottom equation where we made the final equation where N2T
Down
is
here?
equal to, yeah. So where it says 1 minus e to the negative lambda, what is that next to the lambda?
Time.
Oh, 2T times time. Okay, thank you.
So if I gave you a flux, I gave you an initial number of target atoms. You knew the absorption cross-section for that initial target. We could find out the effective decay constant by looking at this. I could run this for a period of time, 2 hours, and I could use this to tell you exactly how many of the, in this case, niobium 94s we would have after the amount of time that we've run it. So what we're showing here is a plot of the curve of this equation. And what I'm going to do on Wednesday is I'm going to pick this up. We're going to work an example so you can see how it works. And then I'll give you a take-home quiz on that that'll be due the following Monday. One little side note before we leave is about, wow, maybe 15 years ago, DuPont Merrick had a production facility up in Mass. And about every other year, I would load up a bus with students and we would go up there to visit their facility. And they had a small reactor up there where they could generate fairly high fluxes, and they made medical isotopes that they shipped around the world. So when we went up there, they might be making Lutetium-99. They could be making anything. They would show us how they made them. They had a fleet of trucks in their parking lot, and they were about 45 minutes from Logan Airport in Boston. And they would make radioisotopes to ship to any medical facility, any hospital, any doctor's office, anywhere in the world. And we would watch them make these products, safely package them, put them on the trucks, and then go off to the airport. We had another half of the trip. We did that in the morning. And then in the afternoon, we went across the street, and there was a company there that made depleted uranium shells for use in tanks. And so these tanks would fire depleted uranium shells. Depleted uranium supposedly is the densest material known to man. And they would fire these typically at another tank. And they were designed so that this material being so dense would go through the armament of the other tank. And once it was inside, it was keyed to explode, which is pretty deadly if you're inside the tank. And they showed us how they received their depleted uranium. Where do they think you got the depleted uranium from? The enrichment of uranium for fuel to go in nuclear reactors. So they took that depleted uranium, which means they've effectively pulled out the uranium-235. So they've taken what's left, which is primarily 238. They shape it into bullets, if you would, and then they make armaments, and then they load those. One of the first problems they had is the material is so dense, they would actually go into the tank, go through the tank, out the other side, and explode on the other side. And of course, that's no good, because you want the thing to explode inside to wipe out the crew. So they showed us how they developed, how they manufactured those materials. This was in Walpole, Mass. They were incredible tours. Since that time, the Merck facility is shut down. They now do their isotope production elsewhere, not in Mass anymore. And the plant that made the uranium armaments shut down due to safety reasons, primarily because of the fine uranium dust when they machine the metals that go into making up the bullet. So they had to shut that down due to health reasons. So none of those are there anymore, but that used to be just a fantastic tour. One other thing of note is the generation facility where you had the neutron flux to create the isotopes actually was on the perimeter of the Walpole State Prison, which is their maximum confinement prison where they keep all the really bad guys. And they put on the fence around this, they said, do not enter high radiation area. And over the entire history of the Walpole, in fact, Walpole is still going, they never had an inmate try to escape over the fence to go through the nuclear facility side because they're afraid of getting irradiated. Just a little side story. That's it for today. You have the one quiz that will be due on Wednesday. I'll be around today till probably 6 or 7 grading the quizzes you just gave me. Will not be in tomorrow. We'll be in on Wednesday. Does anybody have any quick questions for me on anything? Okay, if not, Karen, can I ask you to hang on for just a minute when everybody else goes?